In deep learning-based localization systems, device heterogeneity poses a significant challenge, as varying devices exhibit distinct radio signal strength (RSS) measurement patterns. To address this, the proposed techniques aim to either approximate a function mapping cellular RSS measurements across different devices or transfer knowledge between them. This enables the development of robust and accurate localization systems that can operate seamlessly across diverse devices. The authors evaluate these techniques using 4 independent testbeds, comprising different Android phones. The results demonstrate a remarkable improvement in localization accuracy, surpassing state-of-the-art systems by more than 220%. This significant advancement highlights the potential of the proposed techniques to facilitate the widespread deployment of deep learning-based localization systems across various devices. The proposed function mapping approach enables the approximation of RSS measurements between devices, thereby mitigating the effects of device heterogeneity. Meanwhile, the knowledge transfer technique facilitates the sharing of learned patterns across devices, further enhancing the robustness of the localization system. By addressing the device heterogeneity problem, these techniques pave the way for the development of accurate and reliable deep learning-based localization systems that can be seamlessly integrated into various devices and environments. The research paper addresses the issue of device heterogeneity in deep learning-based localization systems, focusing on indoor localization using cell tower signals. It proposes several techniques, including traditional approaches and novel deep learning-based methods. The authors introduce a general localization model that integrates these techniques, involving the collection of RSS measurements from different cell towers to estimate a probability distribution for various reference locations. The paper highlights the challenges posed by device heterogeneity, where different phones have varying sensitivities to cell tower signals, leading to inconsistent RSS measurements. To address this, the authors experiment with traditional techniques such as linear transformation, which attempts to map RSS vectors across different devices by approximating a linear function. However, they argue that these methods are limited and propose 2 novel deep learning-based approaches. The first technique involves fine-tuning a deep learning model on a few samples from tuning devices after initial training on a primary device, leveraging the universal learning ability of deep models to adapt to new devices. The second technique models the heterogeneity problem as a multitask learning problem, where the model is trained to perform localization tasks for multiple devices simultaneously. The authors evaluate these techniques in 4 different testbeds using various Android phones and report significant improvements in localization accuracy compared to systems without heterogeneity handling. Handling device heterogeneity is a crucial challenge in deep learning-based localization. To address this issue, various techniques can be employed, categorized into traditional approximation methods and deep learning-based approaches. Traditional techniques include calibration, power ratio, and power difference. Calibration involves collecting RSS data from multiple devices to calibrate the model for each device. Power ratio transforms RSS values into relative power by calculating the ratio of cellular RSS readings from each pair of cell towers. Power difference takes the power difference instead of the ratio. Deep learning-based techniques, on the other hand, employ a more complex approach to address device heterogeneity. Transfer learning and multitask learning are 2 such techniques. Transfer learning allows reusing a pre-trained model from a master device as a starting point for fine-tuning the model for another device. This approach is particularly useful when there is a limited number of training samples from the target device. Multitask learning is an extension of transfer learning, where the number of training samples from the target device approaches that of the master device. This technique solves the heterogeneity problem by learning the mapping between RSS and locations from different devices simultaneously. The transfer learning model structure consists of common feature extraction layers and an output layer. The network is trained using a large dataset collected by the master device, and then the model weights are tuned using a small number of samples from the target devices. This approach enables the model to adapt to the heterogeneity in devices, improving the overall localization accuracy. The proposed multitask learning deep model structure, presented in Figure 3, takes cell tower RSS information from different devices as input. It consists of shared hidden layers and task-specific output layers, enabling the learning of relationships between RSS input features and generalization across heterogeneous devices. The performance evaluation of the proposed heterogeneity handling techniques is detailed in Section 4. The experimental setup involves collecting cellular data and GPS ground truth locations in urban and rural areas using 4 Android devices. The data collection process records cell tower identifiers, RSS, and timestamps at a scanning rate of 1 scan per second. The deep learning model parameters, outlined in Table 1, include a learning rate of 0.005, batch size of 40, and 3 hidden layers with sigmoid activation functions. The model is trained using a multinomial logistic classifier with 3 hidden layers, as described in Section 2. The localization accuracy of the proposed techniques is evaluated through 4 experiments, where training is performed using one device and testing is performed using another device. The results, shown in Figure 4 and Table 2, demonstrate that all heterogeneity handling techniques improve system accuracy compared to not handling device differences. The deep learning heterogeneity handling techniques, particularly multitask learning, outperform other techniques, achieving a median localization accuracy of 24 meters, 22 meters, 29 meters, and 26 meters in the 4 experiments, respectively. This represents an enhancement of 220.8%, 286.3%, 1051%, and 1176% in median error compared to training without handling heterogeneity. The improvement is attributed to the ability of transfer learning to capture the mapping between RSS readings from different devices and the combined training between devices, allowing the model to handle noise and generalize better. In deep cellular localization systems, device heterogeneity poses a significant challenge, as features extracted from one device may not be directly applicable to others. To address this issue, researchers have proposed 2 primary approaches: approximating a function to map features across devices or sharing knowledge across different devices. The authors evaluate the effectiveness of various device heterogeneity handling techniques on deep model localization accuracy using 4 independent testbeds. The experimental results demonstrate that sharing knowledge across devices can improve localization accuracy by more than 220%. Specifically, transfer learning and multitask learning outperform other techniques, including linear transformation, power difference, and power ratio. The results, summarized in Table 2, highlight the significant improvement in localization accuracy when device heterogeneity handling is enabled. Transfer learning, in particular, emerges as a promising solution to address the phone heterogeneity problem. By sharing knowledge across devices, the deep model can leverage the strengths of each device, leading to improved localization accuracy. The authors' findings have significant implications for deep cellular localization systems, where device heterogeneity is a common phenomenon. By employing effective device heterogeneity handling techniques, such as transfer learning and multitask learning, researchers can develop more accurate and robust localization systems that can operate seamlessly across diverse devices. Localization technologies have garnered significant attention in recent research, with a focus on enhancing location determination accuracy and efficiency. GSM localization, Wi-Fi-based localization, and quantum computing for location determination are among the prominent areas of investigation. A notable study by Mohammed Ibrahim and Moustafa Youssef, enabling wide deployment of GSM localization over heterogeneous phones, explores the feasibility of GSM localization across diverse mobile devices. The authors propose a novel framework that leverages Gaussian process regression to mitigate the impact of device heterogeneity on localization accuracy. Another significant contribution is dynamic SLAM, leveraging human anchors for ubiquitous low-overhead indoor localization, by Ahmed Shokry, Mustafa Mahmoud Elhamshari, and Moustafa Youssef. This research introduces dynamic SLAM, ASLAM-BASED approach that utilizes human anchors to enable low-overhead indoor localization. By exploiting the mobility patterns of individuals, dynamic SLAM achieves accurate and efficient localization in dynamic environments. Quantum computing has also been explored as a means to enhance location determination. Researchers have investigated the application of quantum computing principles to improve the accuracy and speed of location estimation algorithms. This emerging area of research holds promise for revolutionizing the field of localization. These studies highlight the ongoing efforts to develop innovative localization technologies, addressing the challenges of device heterogeneity, environmental complexity, and accuracy requirements. As researchers continue to push the boundaries of localization research, we can expect significant advancements in the field, enabling a wide range of applications across industries.